This is part 2 of a 2-part episode. Find the first part linked in the description.
Designing, manufacturing, installing, and maintaining the high-speed electronic computer, the largest and most complex computers ever built.
So with signal temporal logic, sounds like you can encode some of these more complex abstract rules of the road in a way that makes sense to autonomous cars and are a set of rules to be followed. Whether those are those are reacting to the right things, it depends on whether the sensors and the machine learning part of the car, as I understand it, is perceiving the world correctly. I'm assuming that there's a lot to get right there as well, and it sounds like you work a little bit on that as well, right?
Yeah, if anything, that's the harder problem to get right.
What makes it? What are the challenges there?
So the main challenge is that it's sort of well understood that deep neural networks, convolutional neural networks or whatever, are sort of by far the best approach that we have for deriving an understanding from large quantities of sensor data, in particular like cameras and lidar. So you can do some things using classical techniques, but deep learning is it's sort of taking over the world, right? And as a result of that, you lose this standard concept of requirements. Well, the requirements are spot every car in the scene and detect every car in the scene. And of course, in machine learning, that's basically expressed implicitly with a bunch of training data and a cost function, when the training data has, bounding boxes drawn around all of the cars. And you're basically evaluating your generalization error once you've trained one of these neural networks. And so your challenge is, I've got this distribution, which is all my training data. It does that distribution, do I do a good job of fitting to that in the network? And is that, representative of the world in which I drive? And so, for example, the most obvious thing is that, all of your training data is from the summer when everybody's wearing shorts and dresses and there's a lot of exposed skin. And then you start to come into winter and it gets a little bit darker and people are wearing hats and scarves. And all of a sudden your detection accuracy for pedestrians drops really badly, or, there's less lighting, or the sun is lower. And in fact, this is a problem we had where, but at a very particular time of the year, the angle of the sun in the UK was such that you would quite often get lens flares on our camera, which tended to look a little bit like traffic lights. And when the angle of the sun was, pointing in that general direction, you would get traffic lights at around the same height in the scene that there would be traffic lights. But they were not traffic lights, they were lens flares. And of course, because we were building a production autonomous system, there are sort of various different modalities that are helping you determine that this is in fact a traffic light or not a traffic light, including maps. But you get these challenges that you don't anticipate, and you turn out to have not quite the right distribution. And so one of the big challenges in autonomous systems is not only just training neural networks with such huge amounts of data to be as accurate as you want them to be, but also then making sure that you have all the data required for the world in which you're driving. And this is difficult. So let me start actually with the actual challenge of training these networks, because it's a good place to start, because in the traditional deep learning world, where you would, use ImageNet or something like that. It's the performance of these systems is, like what percentage of images did I classify correctly? And when you move to networks which are, 3D object detectors, for example, you have traditionally these metrics on the bounding box. So well, let's say a 2D object detector, it puts a box around, a 2D image and it says car. And the idea is that the box has to be very close to the car and it's, getting the dimensions of the car correctly. But traditionally, the metric that the deep learning community use for determining whether or not you've accurately classified this car as a car is something called intersection over union, which is, basically a metric on how much of the bounding boxes are overlapping with each other. So how much of the ground truth, perfect information, overlaps with the region being proposed by the neural network. And, some of the time that number is actually quite coarse, like 50%. And so you could actually have a box which like thinks the car is bigger than it is, or thinks the car is slightly shifted in some way to it is. And so the first thing you have to do in like autonomy for dealing with neural networks is start to get metrics for performance of neural networks that are much more domain relevant. So it's okay actually to do pretty bad at detecting like the size of a car that is 100 meters away from you if you're driving at 30 miles an hour, because you've got time to get a better view of it. It's not okay to make the same error on a car that's like 20 meters away from you. And in certain situations, if the car is in your lane of travel, you need to be pretty accurate. But actually, if it's on a completely different carriageway, well, probably we should be accurate, but like we don't have such stringent requirements. And so, interestingly, what we do at 5 is, and you can almost anticipate this right now, is we use signal temporal logic to also express properties of a perception system. So you can express simple properties, not necessarily needing the sort of temporal aspect of it, but we try to formalize exactly what properties are relevant for us. So
what's an example of something that applies to a neural network that might get things wrong?
So for example, one of the things that we do is we evaluate the domain relevant information in a given image. So where are objects with respect to the road? Are they in the same lane as us? Are they not in the same lane? Are they in front of us? Are they behind us? Are they parked on the side of the road? What types of vehicles are they? What time of day it is? What speed we're driving? And you can say that, for the simplest thing is to say that when vehicles are further away from you, we can accept, a 10% larger error than when vehicles are close. And you can use the temporal aspect of it. So the next thing that perception systems tend to do is they fuse raw detections over time. So instead of just going frame by frame, you end up, classifying this as object 1, and you see object 1 forward and backwards in time, and you can write properties that, express that you don't forget about object 1 or something like that. So you can use some temporal properties there. So like this is the sort of first and easy problem, as it were, to like I call it, based on a paper by some research from the University of Waterloo, calling it partial specification. So it's like doing your best to write some sort of specification for a neural network, and that's sort of what we do there. And then the challenge is to basically show that the network meets that specification in the real world. Because, traditionally you say, okay, I've worked on, faster RCNN, or I've worked on one of these other like super cool CNNs, and I've trained it on this data set, and it gets me this mean average precision, or whatever metric you want to use. It's super good. write my research paper, go to the conference, and we're good. I've advanced the state of the art. And when it comes to, practical uses of these networks, that's basically the first step, right? The way to view the training and the sort of verification of it is like, I'm convinced that it's good enough that I can take it into the world to, to validate it, or so, and so on and so forth. And then actually, to me, that's where the sort of learning journey actually starts, where you're then doing validation in the road or doing validation in simulation and finding where your network is deficient. And in particular, what that's really saying is it's validation. So it's actually where your requirement specification is insufficient. And that's because you're missing images of people in winter style clothing or something like that.
So what do? I mean, the neural network feels like sort of a black box where you put training data in and hopefully good understanding of, for lack of a better word, of that data comes out. But if you recognize a deficiency, is there anything you can do other than attempt to improve the training data?
Yeah. So there's a few different things. So I'll talk about efficiently finding the deficiencies, I guess, first, and then we can maybe touch on, ways in which you can be a little bit more introspective on the black box.
So the first part of the problem you're saying is just even realizing that you weren't getting the quality of data back that you had hoped for.
Yeah. So this is the interesting thing. So let's say we plonk our, let's just be really simple, right? We plonk our neural networks like onto the car and we go out, driving autonomously. And like, as we said before, like these networks are making mistakes all the time, right? And, what you're sort of ideally hoping is that these constraints are staying within the contract, right? They're not too extreme. It's not misclassifying a pedestrian as a bus, and it's not, having, a ghost detection, seeing something that doesn't exist, or potentially worse, not seeing something that does exist, or, thinking something has a very different orientation to what it has. So these are all the problems you find. And, a lot of the times actually, like if you go out and drive with these systems, there will be problems that are quite extreme with the neural networks, but they don't bubble up to a system level problem, either because, it's happened too far away, or it was a very transient problem, or something in the color of the moon and, the sort of flapping of a butterfly's wings means that, this complex system of systems didn't do something bad. And the sort of historical way, the traditional way in which companies started first, testing these vehicles is with safety drivers, where, if the car did something unexpected, it would be reported by the safety driver, either as an event of interest or a disengagement. And then that data would be triaged by engineers and maybe even annotated by humans to give you ground truth. And then you can actually look at the results from the perception system or the neural network and see if they did something wrong that led to that failure. And that's very good, because you'll find these problems, but it's also extremely inefficient, because you basically miss, I'll claim, 99% of the perception failures that don't, in this situation, bubble up to a system level failure. And the argument that I would make is, because we're driving, thousands and hundreds of thousands of miles with these systems in test, once you were to scale that up to a production system that's doing millions and millions of miles, what you would end up with is, some of these situations happening again in a slightly different configuration that leads to a failure. So one of the things that you actually want to do is find these surprises a little bit more efficiently, that even if they don't necessarily bubble up to a system level thing. And there's one very easy way to do that, which is every time your car goes out and drives, you get an army of humans to manually annotate the raw data that came in to get perfect information, and then you can compare the system against it. And you can sort of see that I'm painting two ends of a spectrum, one being, extremely precise, but extremely costly, and one being relatively cheap, but quite imprecise. And some of the work that I've been doing in my research is basically trying to find a middle ground where you can get as much information out of the system for neural network failures automatically and in an unsupervised way as you can to basically help find these edge cases and find weaknesses in the system. And some of the ways we do that is by using other neural networks that are bigger and can take advantage of the fact that once you've actually went and done the drive, you can, sweep backwards and forwards in time. So you don't just have to work with one image. So you can sort of, we call it like pseudo ground truth. So you can automatically get something close to ground truth, which you can then use as a way to find where there are particular failures.
And then there's other ways, I'm assuming, that you're thinking about how to fix some of this sensor stuff as well.
Yeah. So the sort of broad, the way I like to look at it is like thinking about like leading indicators. So in a statistical point, from a statistical perspective, that if you don't have enough data about the lagging indicator of an actual crash or a bad thing, can you use something that's a leading measure of that, which could be like an unexpected failure of the perception system where it fails to meet the contract that you define for it, which I think is the sort of key thing. And so one of the other techniques that we use is that we take all of the data from a vehicle and we make small modifications to it. For example, add a little bit of noise to the image and see how the neural network performs against that slightly noised image. And in general, you'll find that most of the time, the neural network is quite robust to maintaining its prediction under small amounts of noise. So, you can gradually turn 1, 2, 3, 4, up to 10% of the pixels just arbitrarily black and white, but the bounding box for a given vehicle will stay roughly the same because it's not relying on such fine features as it's not the sort of features in the convolutions in the early stages of the network are not so brittle that they can be thrown off entirely by some small changes. But if you're actually quite weak in a certain area, such as we find dark vans against a dark background, or pedestrians that are leaning up against a pole or standing against another type of vertical object, we actually can find that you get quite a divergent behavior of the network once you add noise to it, that actually it doesn't take very much for that detection to disappear altogether or to change shape quite dramatically. And you can use that as some sort of leading indicator that actually probably there's something about this image and something about this pedestrian or this van that makes it quite difficult for the detector. And the challenge, of course, is then, first of all, detecting this type of thing, and then second of all, figuring out exactly what it is that's making it a weak detection, and then figuring out how to iterate a new version of the model that doesn't have that deficiency and doesn't introduce any more deficiencies. So you can start thinking about building some sort of regression test suite for failures of your neural networks and making sure that it never regresses once you find something.
Do the perception systems communicate a sense of their, I guess, do they communicate their own certainty about things to the rest of the system? I mean, so like if you think about, I'm thinking about like, I've got some junk on my desk, right? And like there's a cup over there and it reads, when I'm looking at you, it reads as a blue shape. And like, And then, the rest of my mind's like, well, that's a cut because it was a cut before. And like, it doesn't matter that like maybe it reads as like a blue ball or something. I know it was a cut because it used to be. Is this like, is this just the reality of sensors? It holds true for our eyes. Is it going to hold true for neural networks that are processing various inputs, or is it reasonable to hope to do better in those scenarios?
Yeah, so there are various ways in which you can and should train your neural network to be a little bit more Bayesian, right? To have something like, certainty or confidence in its predictions. And some of the techniques are actually quite inefficient. So one technique is called concrete dropout, which basically works on the point from the perspective of sampling many passes through the neural network for a given image, and what you do is randomly turn off nodes in the neural network, as it were, which is what dropout is, and it's part of a training process that probably we shouldn't get into. But basically, the idea would be that if turning off various neurons in the neural network doesn't have a large impact on the classification or bounding box, then that's a relatively high certainty. But if it has quite a large impact on it, that's a relatively low uncertainty. And there's actually been, a lot of research in the community on, how you can get uncertainties out of neural networks. And recently, there's been a lot of research on, can you actually trust the uncertainties? And people have shown that the uncertainties can be utterly meaningless. It can be extremely certain about something that is extremely wrong about. And people are still trying to figure out why. And, it's neural networks are black magic some of the time.
Well, that sounds like people, though.
Yeah. Yes,
a lot
it's
of
true.
people are
It's very true.
Yeah, I just keep thinking about optical illusions, basically, right? And there's some of those optical illusions where you can kind of grasp how it works, and then there's some of them where it's like, it's so wired into the way we perceive the world that we're just going to get it wrong. Like some of the color ones in particular, and how we interpret color in relative to shadow, for example.
Darks
and this stuff matters obviously for cars as well. But like our built-in model of the way the world works forces us to get that wrong, and there's no amount of additional reasoning that we can apply sort of to override that, which is wild. And I'm sure that lots of people are thinking about whether this is the reality of all perceptual systems, or it's sort of something that we will be able to overcome in the world where we control neural networks.
Yeah, absolutely. And basically, what certainly what we're doing from the point of view of verification and validation is sort of wielding as many tools as we possibly can, and building novel tools to get as good to get your confidence to a certain level. But at the end of the day, we're attempting to build a safety critical system, and you need to in fact have different sensing modalities, so you're not always putting complete faith in neural networks. So for example, you can use free space detectors, or you can use LiDAR or radar or various other different modalities in order to figure out is everything in sync, that there's definitely something there. And that's my sort of research path from formal verification has sort of led me through the safety assurance community. And one of the things that the safety assurance community actually does is they write these things called safety cases, which argue that the system as a whole is safe because there are enough mitigations and barriers that stop, an individual single point of failure from propagating through. And so when it comes to deep neural networks, you will have, redundancy in different sensors, so you can never just rely on one, and you will have monitors in place. So for example, you can have monitors which are checking that the predictions from the neural network have the general shape of cars. So if you think it's a car, does it have the general proportion of a car? Is it driving at the reasonable speed of cars? And so you can like build more and more of these mitigations in place to help you build more confidence. And the challenge is, what do you do when you end up in a situation where you think something's wrong and you have to fail operational? And you know, that's a whole different ball game. But what I'm sort of most interested in and focusing on is how to get confidence in these neural networks and how to start building something a little bit more like introspection into, you know, how they're operating, and find ways to find the failures and understand why that is a particular failure for the network, and how you can then actually start to improve it other than just, you know, plonking that image that previously failed into your training set with, you know, an annotated version of it, so that almost certainly you'll not have that point failure again, but it's, you know, you discover that your network is weak against objects against a dark background, so you solve the general problem rather than the specific problem.
Right. So we're so sort of early on in these neural network applications that it's a big part of the value that you're looking for is just to define where they fall down and where they don't, so that we can try to build reasonable systems around them.
Yeah. Like we're definitely in the early days of applying formal methods and you know, other techniques from the verification community in deep learning, and anybody who has any ideas, send them to me.
I had a quick question about people who might be listening that are putting together quick neural networks from a bunch of data, especially visual, that maybe it's not as critical in terms of safety as you. What are some tips of getting those to function a little bit better?
So the one thing I would say is, like, think carefully about your specification. Really think carefully about, you know, exactly what good performance looks like from a neural network, and what the domain you're attempting to apply it to, and how you can like help the network know when it's outside of its distribution, and because that starts to become more and more important as you rely on that for any downstream task.
And your suggestion of specifying that is then to use it how? To use it in terms of selecting your input data, or like your training data, or change the weights accordingly, or wrap the output around something more sort of that can filter out the results?
So it's a little bit of three things, I think. One is, you know, understanding your training data a little bit better, and understanding the distribution of it. One is understanding, you know, having the right cost function when you're training the network. And then the third is having the right evaluation function when you're sort of taking your verification set.
But you don't need signal temporal logic to write these things down, right? Like if I have a pen and paper, or if I have a markdown file and I set out to say, like, what do I want out of this system? That's going to help me make appropriate decisions along those three axes better, even if I don't have all of the framework that you all have built up. Just being explicit is almost never a bad thing, and taking time to think about your systems.
For sure, though, of course, I encourage everybody listening to your podcast to like embrace signal temporal logic for specifying their life.
Their life.
Their life.
Everything. No, just kidding.
I want to see that.
Always eventually.
That source code document. Eventually floss your teeth.
Always eventually. It's a little better than just eventually.
Well, eventually we should end this podcast.
Yeah. Excellent.
So, yeah, thanks, Iain, for talking to us today. This was so much fun. I could talk about this all day, but we have to stop, and I know it's almost bedtime over there.
Yeah.
So thanks for spending this time with us.
Yeah, much appreciate. Thanks for chatting. See you folks later. Bye.
Yeah,
Bye.
thanks again. This was another episode of Building Better Systems. See you all next time.